Okay, so in this video I'm going to cover a lot of the information that you need to know to pass the physiology part of the exams. There's quite a lot of topics I'm going to go through, so basically I'm going to end up cutting this video into some short, easy to digest chunks so it doesn't get too long. But over this series of videos what I will be looking at is the Greek origins of important words, the respiratory system, hyperventilation, circulation, lung overexpansion injuries, DCS and the benefits of oxygen treatment, the ear, and aquatic life injuries. Once you understand everything I'm going to say about these different topics, you are basically ready to take the exam. So, starting with a little bit of Greek. What is the problem with someone who is hyperactive? And hopefully you are thinking to yourself, they are way too active. So, basically that means that words beginning with hyper mean too much of something. And that actually comes from the Greek language. So, in contrast to that, what is the problem with someone who is hypoactive? Well, hypo means too little. It means not active enough in the word hypoactive. So any word you see starting with hypo means too little of something. The second part of the word will tell you too little of what. So hypoactive, too little, activity, active. So, hyper we now know means too much. Hypo we now know means too little. Well, what other Greek words does it help us to know the meaning of? Capnia relates to carbon dioxide. Oxia, as you may guess, relates to oxygen. Baro. Well, baro, you may be familiar with a barometer, which is something that gauges pressure and converts the reading of pressure and pressure changes to try and give you a way to forecast the weather. So baro means pressure. And trauma. You're probably pretty familiar with that word. It obviously means injury. So putting all those words together and understanding what they mean will actually help you answer quite a few questions in the physiology exam, just breaking the words apart and thinking what they actually mean. So let's put some of this stuff together. Hypercapnia. Hopefully you're now instantly thinking to yourself, well, that must be too much carbon dioxide. Hypocapnia. You're now thinking that means too little carbon dioxide. Hyperoxia, too much oxygen. Hypoxia, too little oxygen. So, we now know what all those words mean by being able to break them up, but now we actually need to be able to picture what these different things, what effect they may have on us as human beings, or more specifically as divers. In order to do that, we need to understand a lot more about the respiratory system. So, the respiratory system. Why do we need to breathe? And maybe you're thinking, we need oxygen. Well, yeah, we do need oxygen. We use oxygen to metabolize food in the same way a combustion engine uses it to burn fuel and create energy. That metabolism takes place in obviously the cells of your body. So we need to get oxygen to the cells of our body so that they can create energy. The waste product of this process is carbon dioxide. And just like a car needs an exhaust, we need to be able to remove the carbon dioxide from our cells. So we need to deliver oxygen and remove carbon dioxide from our cells. And if we don't do that, they will cease to function. So we now know why we need to breathe, but kind of the most important thing you need to understand when you understand these different words we've been looking at is what actually makes us breathe. We don't have to consciously think, breathe, breathe, breathe. Or at least hopefully you don't have to. If I had to do that, I'd be never get anything done because I'm useless at multitasking. So there is actually an internal mechanism that triggers the urge to breathe. There is something in our body telling us to breathe without us having to consciously think about it. Whilst this mechanism is actually very complex, a simplified explanation of it is that it is basically based on the carbon dioxide levels in our body. When the amount of carbon dioxide in our body gets too high, it reaches a certain point, it triggers an urge to breathe. It actually takes place in something called the respiratory reflex center, and the respiratory reflex center says, whoa, the carbon dioxide is getting really, really high, you should take a breath so that we can get rid of some of this carbon dioxide. Which to me is a little bit strange, because I always think of breathing really as a need for oxygen. Okay, yeah, we do need to remove the carbon dioxide, but it seems strange to me that our body is going to determine when it needs to breathe based on having too much of the waste product, rather than determining the need to breathe based on do we have enough of the oxygen that we need. I could also liken it to someone who's about to go to the supermarket and thinking, oh, do I need to buy milk? And rather than looking in the fridge to see how much milk they've got, instead they go through their trash to see how many empty milk cartons there are there, and base their decision on that. So I actually picture this in kind of almost like a gauge. If you look at this gauge here, if you imagine that it is measuring the amount of carbon dioxide in your body, and the respiratory reflex center says that when you reach a carbon dioxide level of 45, I'm going to give you the urge to breathe, and the carbon dioxide level will drop, and then it will slowly go up, and when it hits 45 again, you'll breathe again and drop it, and so on and so forth. That's actually the easiest way for me to sort of explain what I've just described in a more sort of visual manner. So let's take this information and put it together. What we are now understanding is that it's the amount of carbon dioxide in our body that controls our rate of breathing. We also know that hypercapnia means too much carbon dioxide and hypocapnia means too little carbon dioxide. So if we have too much carbon dioxide in our body, it's going to cause us to breathe rapidly and therefore shallowly. Going back to our gauge analogy, you can see there that our body is hitting that 45 point at which it feels the urge to breathe often. The carbon dioxide level is rising rapidly and hitting the urge to breathe point frequently, causing rapid, shallow breathing. In contrast, you could have the situation where you have too little carbon dioxide, and it's going to take a long time before we next feel the urge to breathe. So the gauge on the right here, we got our carbon dioxide level really low, and it's now taking a while for that carbon dioxide level to reach the point at which we will actually feel the urge to breathe. So we still aren't feeling an urge to breathe, we still aren't feeling an urge to breathe, we still aren't feeling an urge to breathe. Finally, we feel the urge to breathe, it drops our carbon dioxide level, and it'll again take a while maybe before we feel the urge to breathe again. So, hypercapnia, too much carbon dioxide. We just saw that too much carbon dioxide can cause us to breathe rapidly and shallowly. And shallowly is a very important part of what I've just said there. By shallowly, I mean taking short short, sharp breaths, if you do that, you realize that with every breath you're taking in, you're not taking that much air in. You're taking a smaller amount of air in than when you just sit and breathe normally. So that is where something else becomes very important, another term you need to know the meaning of, dead airspace. Okay, that problem is bad enough of breathing rapidly and shallowly when we're not using scuba equipment, but when we're using scuba equipment, the problem becomes even greater, and that is because of dead airspace. So we need to understand what dead airspace is. So the actual definition of dead airspace, firstly, your tidal volume is basically the volume of gas you inhale and exhale during normal breathing. But more important is this definition of dead airspace. It is the portion of your tidal volume that plays no direct part in gas exchange. So, what does play a direct part in gas exchange? Well, it's your lungs. More specifically, really, the alveoli in your lungs is where the gas exchange actually takes place. That is where the air that you've breathed in, or the gas that you've breathed in, is actually basically coming in contact with your blood. And it's a kind of semi-permeable membrane, and what happens is that oxygen goes into solution in your blood, and carbon dioxide comes out of solution and turns back into a gas into your lungs for you to then be able to exhale it. It's all to do with the fact that pressures always want to equalize, and we're going to look at a little bit of that in more detail later on in the presentations. But the important thing to realize right now is that the alveoli in your lungs are the only place where gas exchange occurs. So, when you breathe, obviously the air is passing through your regulator or your snorkel. It's going down into your mouth, down your throat, and it travels quite a long way before it actually gets to the alveoli. So when you inhale, you've got to imagine that a bit of air gets to your alveoli, but quite a lot of air actually never reaches it. It fills up your throat and your mouth, and even your regulator or your snorkel. And when you then exhale, obviously you don't exhale all the air. There is still a bunch of air left in your throat and in your mouth and in your regulator. And the next time you inhale, that air that you previously exhaled is pretty much the first air coming in and going into your lungs. And the problem is that that air that you previously exhaled is going to be high in carbon dioxide, the waste product, and low in oxygen. And that is where dead airspace can become a problem. As long as the amount of air that is going into our alveoli with every breath, if only a small amount of that or a small percentage of that is dead air, air that we previously exhaled, then there is no problem. But if it's a high percentage of air that is going into our alveoli is dead air, then we're getting lots of air that's high in carbon dioxide and low in oxygen and not very much good air, and that creates a problem. So basically, rapid shallow breathing will mean that there is a lot of air going into our lungs, which is dead air that's high in carbon dioxide and low in oxygen. And that is basically going to mean that our CO2 levels remain high. Breathing rapidly and shallowly means that we have a higher CO2 levels than if we breathe normally. So it's a vicious circle. So let's actually try to understand a little bit more about that. I'm quite a numerical guy, so I'm actually going to try and sort of apply some very random, factually incorrect numbers to this, but they do illustrate the point I'm trying to make. Let's just say that the volume of our mouth and our throat is half a litre. If you're imperial people, call it, I don't know, half a pint. Let's say that when we breathe normally, we suck in what passes our lips with every inhalation is 2 litres of air. Imperial people, 2 pints. Dead air makes up half a litre. So what we basically just said there is that 25% of the air we are breathing in is dead air. Quarter of the air we are breathing in with every breath is high in CO2 and low in oxygen. Now, let's imagine that we're breathing rapidly and, more importantly, shallowly. So what's actually happening is, instead of the normal 2 litres of air we breathe in with every breath, we're actually only breathing in 1 litre of air with every breath, shallow breathing. And that means that if the volume of our dead airspace is half a litre and we're only breathing in 1 litre with every breath, it means that 50% of the air that we're breathing in with every breath is dead air, which is high in CO2. And that is going to mean that our CO2 levels end up higher than normal. And that can cause us to feel the need to breathe even more rapidly and even more shallowly. And the problem will get worse and worse and worse. It's this picture here of our CO2 level hitting the need to breathe quickly and us going rapidly breathing. So let's imagine a different situation where we deliberately, we actually mentally make the decision to breathe extremely deeply, more deeply than normal. If you imagine yourself breathing in and filling up your lungs as much as you possibly can, that's what I'm trying to describe here. So obviously you could maybe inhale much more air than you normally do with normally breathing by deliberately breathing deeply. Let's imagine you manage to breathe in 4 litres of air with a very, very big, deep breath. Now, of course, that 0.5 litres of dead air only represents 12.5% of the air you're breathing. So what you're actually doing is breathing in a very small percentage of air that is high in CO2, much smaller than normal. So you are, by doing that a few times, if you were to take 10 or 15 really big, deep, deliberate breaths, you would actually be lowering the amount of CO2 in your system deliberately. And the effect of that will be that you will not feel the urge to breathe, the animal instinct that's telling you you need to breathe. You will not feel that for a longer period of time than if you had just breathed normally. And that is, in fact, the reason why freedivers actually do hyperventilate, voluntary hyperventilation, big, deep breaths, a few times before they do a breath hold dive. It's going to lower their CO2 levels, and it's going to delay the urge to breathe for a while, allowing them to stay underwater longer. And again, you probably don't need to see this, but what I'm picturing is someone who's dropped their CO2 level way, way down, and it now taking a while before it reaches that 45 mark when your body tells you you've got to breathe. So, we've talked about rapid shallow breathing, and that is usually an involuntary thing, and it results in a high CO2 level. And that causes you to potentially want to breathe even more rapidly and shallowly. We've then talked about very deliberate, deep, slow breaths that are actually going to lower our CO2 level, artificially lower it to below a normal level. And that's going to result in us feeling a delayed urge to breathe. And that would be voluntary hyperventilation. So rapid shallow breathing is an involuntary response caused maybe by overexertion. You've all felt that rapid shallow breathing after running a race or going jogging or doing exercise or whatever. Obviously, another example, another thing that could cause rapid shallow breathing, or at least shallow breathing, is a poorly adjusted regulator. If you've ever actually tried to breathe from a regulator that's quite difficult to breathe from, and you're actually really having to kind of suck on it to get it to deliver air, well, if you picture that, every time you're sucking on it hard to get air, you're going to end up getting a smaller amount of air than normal. So you're inhaling a smaller volume of air than normal, and therefore the percentage of dead air that you're breathing with every breath is higher. So both of those things, overexertion and poorly adjusted equipment, such as regulator, are going to cause involuntary hyperventilation. The opposite of that is voluntary hyperventilation, a deliberate mental act where we deliberately breathe very, very deeply, trying to fill our lungs as much as we can possibly fill them, and we do that repetitively. What we're doing is lowering our CO2 levels and delaying the urge to breathe by reducing the amount of CO2 in our body to artificial lows. So, don't want to labour the point, but so many questions in the physiology exam can be answered by your understanding of this and reading the question carefully. When you see a question that's talking about involuntary hyperventilation, you need to picture someone who is breathing rapidly and shallowly, maybe as a result of overexertion, maybe as a result of having a bad regulator that's difficult to breathe from, but they're breathing rapidly and shallowly, and as a result of that, the amount of CO2 in their body is increasing steadily, and that's causing them to want to breathe more and more rapidly. Voluntary hyperventilation, when you see these words, you need to picture someone who's about to go on a breath hold dive, who's breathing very, very deeply, deliberately. They're doing it because they want to decrease the level of CO2 in their body, which is going to delay the urge to breathe and make them able to stay underwater, holding their breath for longer. Involuntary hyperventilation can lead to hypercapnia, too much carbon dioxide. They're breathing shallowly and rapidly. A lot of the air they're breathing with every breath is dead air. That dead air is high in CO2, resulting in too much CO2 in their body. Another word for that is hypercapnia. Voluntary hyperventilation can lead to hypocapnia. They're deliberately breathing really slowly and deeply. They're deliberately lowering the level of CO2 in their body. And they are potentially lowering it to the point that they don't have enough CO2 in your body. Now that might be a difficult thing to get your head around. How can not having enough of a waste product be a problem? We just talked about carbon dioxide being a waste product, something that we're wanting to get rid of. How can you have too little of a waste product, too little of a bad thing? Well, of course, if you have too little carbon dioxide, even though it's a waste product, the urge to breathe is delayed, and it might just be that your urge to breathe is delayed for so long that in the space between taking breaths, you actually metabolize too much of the oxygen that's in your body, and you end up with not enough oxygen in your body, and that is obviously a very big problem. So hypocapnia means too little CO2. It means the urge to breathe is delayed, and it's delayed excessively. The oxygen levels in our body may get too low because we are not breathing often enough. We need to get that oxygen pumping around our body. What happens if we have too little oxygen in our body? Well, too little oxygen in our body causes us to lose consciousness. We actually black out. What is too little oxygen called in Greek? You got it, hypoxia. Okay, so if we do not have enough oxygen because we didn't breathe, because we didn't have enough carbon dioxide to give us the urge to breathe, but we did actually need to breathe because our oxygen levels were getting too low. So basically, the problem with excessive, deliberate, voluntary hyperventilation is that we create a state of hypercapnia. We don't have enough carbon dioxide, we don't feel the need to breathe, and as a result of not breathing, we end up with not enough oxygen in our body. We end up with hypoxia. So, you may be realizing now that what I'm really talking about here is shallow water blackout. So, shallow water blackout comes back to stuff you hopefully know from the physics part of the dive theory study. imagine that you voluntarily hyperventilate. You create a situation where you have hypercapnia, not enough carbon dioxide. You are not feeling the urge to breathe for a long, long time. So let's imagine you create that state of hypercapnia and you then do a breath hold dive and you dive down to a depth of 20 meters. What is the pressure at 20 meters? Hopefully you're all shouting at the screen 3 atmospheres. So you're under 3 atmospheres of pressure and then you start ascending. So now what we're going to do is we're going to try and actually draw something which is explaining why we black out in shallow water. All right, it's all to do with the falling partial pressure of oxygen as you ascend. Key thing to remember, shallow water blackout is caused by the falling partial pressure of oxygen as you ascend. So let me try and use some of your physics knowledge to actually explain what that statement actually means. So basically, let's just say, for argument's sake, the point at which you will lose consciousness is when your oxygen partial pressure, your blood oxygen partial pressure, falls below 16% or 0.16 atmospheres. All right. It's at that point that you will lose consciousness. All right, and we are doing this breath hold dive. We're diving down to 20 meters and swimming around down there. And while we swim around down there, we metabolize oxygen. And we're down there long enough to actually get our blood oxygen percentage down to 10% blood oxygen, or 0.1 atmosphere. But because we're at 3 atmospheres, it feels to our body, our actual oxygen partial pressure is 30%, or 0.3 atmospheres. So the depth we're at means that we've managed to reduce our blood oxygen level below the point at which we would stay conscious, because the pressure we're under, it increases the actual oxygen partial pressure. So then as we start ascending, we ascend up to 10 meters. We're now under 2 atmospheres of pressure. It is now like our blood oxygen level is only 20%, but that's still enough to keep us conscious. When we hit 5 meters, which is 1.5 atmospheres, our blood oxygen level is still only at 10% because we were swimming around down there at 20 meters for a while. Now, suddenly, the partial pressure of the oxygen in our body has fallen below the threshold that allows us to remain conscious. We black out, shallow water blackout, sudden loss of consciousness, and it is because our blood oxygen level has got too low. We are hypoxic. Okay? That's what's actually happening. So hopefully you're now understanding why the blackout happens in shallow water. As we ascend from a dive, the pressure we're under falls, and the fact that the pressure we're under is falling also means that our oxygen partial pressure in our body is falling. And when our oxygen partial pressure in our body drops below approximately 16%, we lose consciousness. So now, hopefully visually, you're starting to understand that as we ascend, the partial pressure of oxygen in our body falls. Even though we've got the same actual oxygen percentage in our body, the partial pressure is falling because the pressure we're under is falling. And when it falls below a certain point, we lose consciousness. And as long as you understand that, you understand why the blackout happens in shallow water. You also need to think about the descriptive terms that we could use. It could be, we could refer to it as shallow water blackout. What's actually happening is we're suddenly losing consciousness. We are suffering from hypoxia. We are becoming hypoxic. We no longer have enough oxygen in our body. All of these terms basically mean the same thing. So, let's now have a look at hyperoxia, too much oxygen. Alright? Well, hopefully what's jumping to mind is exceeding a safe partial pressure of oxygen. And you're exceeding a safe partial pressure of oxygen by diving too deep for a given blend. So basically, if you've done your nitrox certification, you'll understand that we plan our dives to not exceed a 1.4 atmospheres oxygen partial pressure, and as a contingency, in case something goes wrong down there, we also know what the depth would be where we reach 1.6 atmospheres, and make sure that we never, ever, under any circumstance, exceed 1.6 atmospheres partial pressure of oxygen. Why do we not do that? Well, because at 1.6 atmospheres partial pressure of oxygen, we've got too much oxygen. We're suffering, we've got hyperoxia, and it can cause CNS oxygen toxicity, which is basically a sudden convulsion underwater. You'd spit out your reg and you'd drown. It's sudden death. So there is another type of oxygen toxicity. It's called pulmonary oxygen toxicity, when you expose yourself to too high a concentration of oxygen over a period of time, and that has symptoms of, coughing, irritated lungs, painful chest, that sort of thing. It's extremely rare in diving. It happens more to people who are maybe in ICU units in hospitals and being given high concentrations of oxygen over many days. But there is something that people who are technical diving need to be aware of. If they're breathing 100% oxygen for deco stops for excessive periods of time, they could expose themselves to too much oxygen and suffer from pulmonary oxygen toxicity. But your average diver, their concern with oxygen toxicity is CNS oxygen toxicity, and that is avoided by never exceeding a partial pressure of oxygen of 1.6 atmospheres. So, one of the things we need to make sure we understand as we continue on with this part of the physiology is your body's demand for oxygen. What determines how much oxygen your body needs? And the answer to that is basically your level of activity. Remember, the body's demand for oxygen has nothing to do with the way we breathe. It has everything to do with how much activity our body is doing, how much energy our cells need to produce. So basically, physical exertion is obviously going to result in our cells, particularly our muscles, needing energy. Our digestion, our digestive muscles, if we've eaten a big meal, are going to be working pretty hard, and they'll be needing to burn oxygen to be able to do their job. But the way you are breathing has no effect on your body's demand for oxygen. So when you see that question in the physiology exam, which is asking about how voluntary hyperventilation extends a breath hold time or something along those lines, don't fall into the trap of choosing the answer that it reduces your body's demand for oxygen. Voluntary hyperventilation does not reduce your body's demand for oxygen. The only thing that reduces your body's demand for oxygen is how much activity you're doing. Just stopping and resting would reduce your body's demand for oxygen. Hyperventilation doesn't reduce your body's demand for oxygen. What it does is it lowers the carbon dioxide level in your body, fooling you into not thinking you need to breathe, even though you actually may need to breathe in order to keep your oxygen levels at the required percentage to stay conscious. Okay, so that is Physiology Part 1, brought to you by Coconut Tree Divers and GoPro Caribbean. I want to emphasize the importance of understanding what we put there. It basically will help you answer probably 25% of the questions that you get in the physiology exam, just this video I've done. I'm going to be doing a few more videos to cover the other information you need to know. They'll be coming over the coming weeks. But what you've just learnt there literally is about 25% of what you need to know. If you're finding this video useful and the other videos I've made, please, if you want to help me in return, on any website you own, on any blog you have, if you're posting in forums describing your experience of becoming a dive master or becoming an instructor, if you can link to my website, www.goprocaribbean.com, that is the best thing you can possibly do to help me in return.